Hi guys, and welcome back to Elevate Chem. It's Jesse with another concept video. Now this is our second in our 5-part series, which will be looking at stoichiometry, and is really designed to wrap up all of the content that we've looked at so far. Now as always, we're going to be looking at an exam style question because ultimately that's the best way to take in this information and really understand these concepts and how it's applied in an actual exam. Now the first thing I want you to do is to have a go at this question. It's from the VCE 2010 chemistry exam number 1, and it is question 1. So pause the video now, have a go, and we'll have a look at how this question can be done when you're done. Fantastic. Hope it went well. So, right off the start, there's a lot of content given here, and you'll find that for stoichiometry questions, this will be a recurring theme. First thing I always do is actually skip to the first question itself, because I don't know what information I need yet. So it says here, write a balanced half equation including states for the conversion of MnO4 ions in an acidic solution to Mn2+ ions. So, we're actually given some additional information within the question, but we don't even really need it. Write a balanced half equation for the conversion of MnO4. So I'm going to write that on the left-hand side of my equation to indicate that it's one of the reactants. And it says it's in an acidic solution, so I know it's in an aqueous state. I'm going to draw an arrow slightly further along in the page in case I need any species here. And I know it's converted to Mn2+, and again, that's going to be in some sort of solution, so I'm going to indicate that it's aqueous. So, we need to now include some other species, and how we're going to do that is simply from balancing out this reaction. So we can see on the left-hand side that we have 4 oxygen atoms. And that means on the right-hand side, we're going to need additional oxygen atoms. And when it comes to balancing half equations, the way in which we do that is by adding water. And the amount of water I'm going to have to add is 4 moles of water. And the reason why is that because, of course, that means we'll have 4 moles of oxygen there. So now I need to balance out my hydrogens. So I've got 8 hydrogens on the right, so that means I need to add 8 hydrogens on the left. And again, they're going to be aqueous. Awesome. So I've now balanced each of my elemental species out. Now I have to check for my charges. So on the right hand side, I've got an overall charge of 2+, and on my left hand side I've got an overall charge of 7+. That means I'm going to need to add 5 electrons to the left hand side of the equation to balance that all out. Fantastic. Now often you'll see that the electrons should be written on the furthest right, or rather as the last reactant in your reactant series, but ultimately it doesn't matter if your electrons are written over here, in the middle, or on the right hand side. It really doesn't matter. Awesome. So that's all I need to do for that part of the question. I haven't really need to read any of this information yet. B. Calculate the average volume in mil of the concordant titers of the potassium permanganate solution. Okay, I'm going to have to start reading this question now. But I know I'm looking for titers, and I know I'm looking for mils. And I can see up here there's a little bit of talking about mils here, there's some talk about mils here, but then it's talking about titrations, and I can see that here we go, here's titration numbers, and here's volumes. And all it's asking for is the average volume. So all I need to do is simply calculate the average. How we calculate the average is by adding the values together and then dividing by the total number that we've got here. Now, we need the concordant values only, and these means that the values are closest to one another. So we're actually going to be ignoring this value of 20.25 as it's not similar to those other values. So the concordant values are 22.03, 21.97, 21.99. Taking an average of those, again, is simply adding them up. So I'm going to say V av equals 22.03 plus 21.97 plus 21.99, all divided by 3, and that gives me an average titer of, amusingly enough, 22.00 mils. And the reason why I'm leaving in the 00 there, guys, is because everything else has been to 4 significant figures. That was 4 significant figures, 4 significant figures, 4 significant figures. This 3, because it's an exact whole number. It was a number of counting, not a number of measurement. That means it isn't included when you're considering significant figures. Alright, moving on to the next part of the question. Use your answer in part B to calculate the moles of MnO4 aqueous ions using this titration. Okay, we're definitely going to need to start understanding the rest of the question here. So we're looking at titrations, and it was a titration volume of potassium permanganate used or recorded in the table below. So reading through this information, how we're going to get the moles of MnO4 is simply by obtaining the concentration times by the actual volume itself. So if you notice, what we're looking for is MnO4 ions, and this is KMnO4. So that means that we're going to be using these titers to calculate the number of moles. So moles, N, is equal to C times V, where C is our concentration in molarity, and V is our volume in litres. So that means we need to find the concentration for MnO4. And we see that within the question, it is stated right here, the concentration is 0.04. Now this is 0.04 of the potassium permanganate solution. So how do you know what the actual concentration is of the permanganate itself? Well, if you were to allow this to dissociate, you would get K plus and MnO4 minus ions. Notice that this is a 1-to-1 ratio. For each KMnO4, you're only going to get one MnO4 ion. And that means once the substance has dissolved, once the substance has dissociated, you're going to have the same concentration of MnO4 minus as you are of the original substance. So that means the concentration was 0.04, and of course that was with 2 more zeros afterwards to ensure significant figures, times by the volume in litres, so 22.00 by 10 to the minus 3. And that gives us a final value for 8.80. That additional 0 is simply to account for significant figures, times 10 to the minus 4 moles. Now, how did I know it was 3 significant figures? Well, although my volume had 4 significant figures, my concentration simply had 3. So that means that my final answer is only as accurate as the least number of significant figures in my calculations. So that means 3 significant figures should be in my answer. So moving on to the next part of the question. Calculate the amount in mole of Fe2 plus ions present in the 250 ml flask. Well, we know that the amount of moles in the 20 ml aliquot, because that's what we were titrated against, 20 ml aliquots of this Fe solution were titrated against the 0.04 molar potassium permanganate solution. So we know that there must be a relationship between the number of moles of Fe2 plus in this aliquot with the number of moles titrated against. We can actually see from this equation that there is a 5-to-1 ratio. So that means moles of Fe2 plus in the 20 ml aliquot is equal to 5 times the moles of MnO4 minus. We can calculate that simply to be 5 times the 8.80 by 10 to the minus 4, and that gives us 4.4 by 10 to the minus 3 moles. But that was only simply in the 20 mils. So if we know that's in the 20 mils, the moles of Fe2 plus in the 250 mils, and because it's an aliquot, guys, there's no change in concentration. So that means that we simply multiply by the relevant ratio. And what that ratio is going to be is 250 divided by 20. And the reason why is this is our final volume, and that was our initial volume. And again, because it's an aliquot, there's no change in concentration, so you simply need to account for the change in volume using that fraction that I've just written there. And that's multiplied by 4.4 by 10 to the minus 3, and that gives us a final value of 5.5 by 10 to the minus 2 moles. Awesome. Fantastic. Apologies, there should be a 0 in there. Although this value right here doesn't actually need a 0 in it, and the reason why is because as you go through these steps of working out, significant figures aren't important. However, your final answer must have the correct number of significant figures. Make sure you remember that, guys. Now, part E, calculate the percentage by mass of iron in the 80.50 gram sample of alloy. Okay, so now we're going to need to wrap up this question and finally work out this answer. Well, we know the moles in this alloy is equal to the moles that we just found above. And the reason why, if we read through the question, it says an 80.5 grams of alloy is dissolved in concentrated hydrochloric acid, and that solution is transferred into a 250 ml flask. So, if the solution is transferred into this flask, that means this solution has the same number of moles, and that means that this sample has the same number of moles as well. So we know that the moles of iron in this alloy is equal to 5.50 by 10 to the minus 2 moles. And from that we can work out the mass. So the mass of iron is equal to the moles times the molar mass. So that is equal to 5.50 by 10 to the minus 2. Grabbing the molar mass from our periodic table, so times 55.9 equals 3.07 grams. Again, at this stage, I'm not concerned with significant figures. So therefore, percentage mass of iron is equal to the mass of iron divided by the total mass of the alloy. So it's 3.07 divided by, the total mass was 80.50, written just here. And then it needs it as a percentage, so I'm going to multiply that value by 100, and that will give me a final percentage of 3.82%. Now notice there might have been some rounding here, so you might have potentially gotten 3.81. And notice finally that I have 3 significant figures here, as that is the least accurate value that I have. Fantastic, guys. Hope that all went well for you, and I hope you got something out of it. Some key things that I want you to note once again is that for these stoichiometry questions, often there's a lot of text written, and I highly recommend looking at the questions first and identifying the information that you need. However, once you get to a stage when you're starting to wonder what is the big picture here, do read through the whole question and see if you can work out each of the individual steps here. I often think it's often useful as well to actually draw a diagram and potentially draw out a little block of your alloy sample here being dissolved into a flask. The flask is at 250 mils, showing that you're taking a 20 ml aliquot and then titering that against the 0.04 solution. However you want to draw this process, often it's useful to actually draw a diagram so you can see almost like a flow chart of what's happening. Fantastic, guys. I'll see you in